So, hello everyone. This is a series of a couple of introductory talks to Sandpiles with an emphasis on the movies. So not only pictures, but uh, the things moving. So, this is called Introduction to Sandpile Movies. Okay, let's say part one. So I don't know how many parts there will be. So Sandpiles deserve much more detailed introduction, but still I'll first address the question, why bother? So very quickly, why study Sandpiles? And depending on where you come from, there can be different answers. The most pedestrian or closer to, usefulness would be to say that it is a prototype of self-organized criticality. And there is a lot that can be told about that. Well, basically, this is type of complex system, let's say, demonstrating power laws without being finely tuned, or between order and chaos, of course. So I'm not speaking about that much, but really, many people think that studying Sandpiles would allow understanding better natural phenomena like earthquakes or avalanches in neurons in the brain or solar flares or many other things. A little bit more close to us would be to say that at least in some cases, let's say starting dimension 3, maybe in 2 as well, it is Turing complete. Which also justifies that Sandpiles are hard. So it's not easy to study Sandpiles. Like essentially any computational problem can be reduced to Sandpile configurations. Another answer here to mathematicians would be to say that it's mathematically diverse. Okay, so when you study Sandpiles, you can come with very different backgrounds. You can come from combinatorics or algebra or probabilities or mathematical physics or differential equations or geometry. So me personally, I'm coming from that part. And then probably to me, the most important reason, and so I'll justify that in a second, is that it's simply beautiful or attractive visually. Okay, and let me justify just that. Um, so now I'll show you one picture. And yeah, so this small picture is the Sandpile identity element. So there is some group that I'll recall in a few minutes. And this is an identity element. And colors mean some numbers. So there are only 4 colors, 0, 1, 2, and 3. So 3 is black, 2 is blue, green is 1, and white is 0. And so one thing that you notice about these pictures that they are scalable. So this is for scale 100, and that will become clearer afterwards, what it really means. So this is for the scale 200, and this thing is for the scale 300. And one thing you want to formalize about this picture is that it converges. And probably the easiest convergence for stating purpose would be weak star convergence. But today I'll just say that in certain situations, this is certainly not enough. This is definitely too weak to capture the intricate phenomenon. And yeah, so I guess there is no still no consensus on this result about the convergence of this kind of element, but it's easy to admit that it's beautiful, it's intricate, and at least there's certain structural phenomena they are still not proven. So there's this field has a lot of wide open questions. And closer to the topic of what I was going to speak today is the following thing. And this is a type of movie, and this is probably the simplest movie I've ever seen in these sandpiles. And for a couple of weeks, I was thinking about it. So let me run it. So indeed, it's much simpler than the previous pictures. And this is an advantage that probably this thing can be described totally explicitly. And next time, I hope to explain it in detail. Today, I'll just state some of the results, like weak star convergence, which would be idiotic. And then I would show how to improve it a little bit so that at least there will be some qualitative uh, means to determine at what time you are in this movie. So this movie runs from 0 to 1, the time, and given a time frame, given a frame, I want to be able to say explicitly at what time you are seeing it. Okay, so yeah, mesmerizing, but still simple. And the thing is,
Here
there,
in this movie, the resolution is fixed, of course.
what?
So sorry, in this movie, the resolution is fixed, of course.
Yes, it was fixed, but the claim would be that the movie converges and even stabilizes.
Uh-huh, uh-huh.
Uh,
And
i-
as you scale this, as you scale the movie keeps looking more the same,
yeah,
and then uh, well,
well,
you'll make a statement
it
about that.
will be very similar. But next time we will discuss in a lot of details. So now I wanted to briefly sketch the most basic definitions in Sandpiles. And for that, let me start with gamma. So there are different letters. I prefer gamma. And for us, for now, it will be a subset of the square lattice. In principle, it can be any set of vertices of any graph. And of this square, we actually think as a graph where we connect by horizontal and vertical uh, edges. So you imagine that you connect like that. And for us, this gamma will be some portion of the lattice. And later it will be important that there is some part of this gamma which is the boundary. Okay. Now, a state on gamma will be simply a function phi from gamma, let's say to non-negative integers. And we call it stable if actually it takes only those four values we talked about. Um, okay. And now I define the crucial local rule, and there is a single local rule in the whole model, which is called the top link. So if you have some unstable state, so meaning that there is some particular point where the value is greater than 3, then we perform a top link. Top link at V. So, and let me draw the picture for that. So you have this piece of lattice, and at some point you are greater than 3. And now you do this top link, and you reduce by 4 at this point, and you add 1 to the neighbors. And if you are at the boundary, you simply lose 1, let's we say, grain of sand. So the number of values, the total one decreases if we do toppling near the boundary. Otherwise, it is preserved. And one way to think about the toppling, it's adding the Laplacian, discrete Laplacian of the delta function. Yeah, and you can think of this as a definition of Laplacian as well. So now these topplings, they integrate to a global creature, which is called the relaxation. And relaxation is doing topplings until the state becomes stable. So a few facts you should be aware of. This relaxation always terminates if the set is finite, and the result of the relaxation denoted by phi 0 doesn't depend on the particular order of topplings. This is one of the reasons why people also add adjective abelian to the Sandpile model. So, but currently, I guess there is no non-abelian Sandpile model, but abelian also means that there is some abelian group floating around, and we just go to this. So we go to recurrent states. Which will constitute a specific abelian group of states on gamma. So recurrent state is something which is obtainable from any other state by adding sand grains, so by increasing the values, if you like, and relaxing. So a couple of remarks. First remark is that all three, so the maximal stable state, which you can denote like this, all, so it takes only threes as values, is recurrent. And actually, you can say, instead of adding sand grains to any other state, you can say that it's obtainable from all three by adding grains. And there is also another thing, there is a test. So there is a test for being recurrent. So phi is recurrent if and only if phi is equal to phi minus Laplacian of 1, and then relaxation. So this minus Laplacian of 1 is supported only along the boundary. It takes generally values 1 and 2 on the square. So on the square, you could think of 2's in the corner and 1's otherwise. So you add this thing and you check if your state is recurrent. You can check easily for all three. And for us, it will be important also to check it for all two. So this is an easy exercise. Use this criterion to check that the all two state is also recurrent. Okay, then the Sandpile group, G of gamma, is consists of all recurrent states. So this is Sandpile group. And the operation is basically pointwise addition followed by relaxation. So this is the operation. And it's easy to see that this group is abelian. Also, it's finite. And the funny thing also is that the identity element, so unless gamma is a single point, the all zero state doesn't belong to the Sandpile group. And it's easy to see, right? From what I told you, you add, so you use this criterion. So you add to zero this thing, there is nothing to stabilize. It's not, again, all zero, therefore zero is not recurrent. So there is some other thing serving the identity element. And that beautiful pictures, remember, with the square and some kind of fractals, this was exactly the identity element on the square. And there is a formula for the, neutral element. In G of gamma, and this formula, an easy exercise to verify that it is true. So you take all six state, then you subtract the relaxation of all six, and then you relax again. So this is the identity element. Although we have a formula, it doesn't help that much. So actually using a version of this criterion is actually more helpful. So you just add the same thing many times until you stop changing. And this is a way to approach the identity element used by Michael Kreutz originally. Okay, and now I also tell that as an abstract group, you can find an isomorphism which is just the co-kernel of the Laplacian. So you quotient by the image of the Laplacian on all integral value functions, but this way you lose pictures. And here, for example, the identity element will be just exactly the class of the zero element. So this is not very interesting, but sometimes it's useful to think of this isomorphism. So yeah, that's all I wanted to tell about recurrent states and Sandpile group. Now I pass to further thing, namely the movies. Now I tell you what are the movies, Sandpile movies. So first I define this thing, which will be the extended Sandpile group. So you can think of it as recurrent states which are allowed to have real values, but only along the boundary. So a priori, it's not clear that this thing is connected or that maybe there is a well-defined group structure, but I claim it's very easy to show that if you just allow all your states to have real values and not simply real values, but so phi of it should be also stable, so it should belong to the interval from 0 to 4. Now, what I wanted to tell that in this particular case of lattice subgraphs, G tilde of gamma is always connected. It's a torus of dimension equal to the number of points at the boundary. This is not very surprising, but surprising, at least when we were discovering this, was the magic property mainly some kind of functoriality. So if you have two domains gamma 1 and gamma 2, then there is a epimorphism, so surjective homomorphism from the bigger domain to the smaller domain. And this kind of thing you don't have at the level of the usual sample group. And now the movie, a very well-baked general definition, is just a path on G tilde gamma. Reality. So this is very general definition. So you take whatever path on your continuous group, you see the pictures moving, well, that's a movie. But then there is a more industrial way to produce movies. And for that, you pick a harmonic function. So H is a discrete harmonic function. Then if you have also some initial state phi, and also you have some time t, you define the movie at time t as phi plus t times the Laplacian of the restriction of this h to gamma. Oh, and then you relax. So this it also Moritz Lang called harmonic Sandpile dynamics. I'll just basically call it harmonic movie. And important thing about movies is that any two states on a given domain can be connected by some harmonic movie. And by a movie, even harmonic movie. And this is, for me, the reason to study them, because it can be turned into a tool to approach all those pictures and Sandpiles. For example, my dream would be to start with something very simple, like all three maybe, or all two, and connect it to the identity element and sort of reconstruct what's going on by means of this dynamic approach. And so now I wanted to go to the simplest movie. And first, maybe
You repeat that sentence that you just said? What was?
the sentence that movies can be used to connect different elements of the same Sandpile group. And you probably can discover how the things are transformed. And my goal would be to go to the simplest movie and start exploring from there. Also, I wanted to emphasize that there is an hierarchy. This gives hierarchy on the states. So you can start with some state, and then you can ask of what degree this harmonic potential, this H can be called potential, should be to connect to given states. And in this couple of, well, few talks, I'm going to describe more or less explicitly the linear potentials and the simplest kinds of states. And the simplest, it appears, is all two. We just saw that it's basically made of strips. Okay. So maybe for today, I'll just state the result. So there is probably no need to recall what is weak star convergence, or there is a need to do that. You think, guys? Should I tell what I mean by weak star convergence, or?
For the video, it takes 2 seconds.
Okay, let me, yeah, so let me just recall weak star convergence. And for that, I'll be thinking about a family of graphs, gamma n, let's say n times omega intersection with d square, where omega is some domain on the plane. So gamma n is a sequence of bigger and bigger domains. And assume that we have some functions phi n from gamma n to r. And first thing, to formally speak about convergence of phi n, we need to pull it back to the omega, to the honest function, because now the definition of such thing is discrete. So for that, I take phi n tilde, the function now on omega, going to, again, to r, and define it in the following way. Phi n of xy is phi n of the scaling and the floor of each coordinate. And now I say that phi n converges big star. So phi n star converges to, let's say, phi infinity, big star sense. And by the way, this phi infinity in what I'll be saying today will be just a function, but in principle, it can be some distribution. So some things like delta functions, so measures supported on some linear spaces like graphs. But let's assume for the moment just a function. So big star converges if for any test function psi C infinity on omega with support of psi in the interior, the integral of phi n tilde times psi times dx dy, so on omega converges as n goes to infinity to same integral phi n tilde, no, phi infinity psi dx dy. Okay, so I better should write like phi infinity of psi, so that would be more accurate. So for example, example would be delta f0 or some point p of psi would evaluate psi at this point. And this is not a function, this is really some, well, distribution, direct delta function. Okay, so this is star convergence, and now I pick the simplest movie and tell you what would be the limit, the star limit for this kind of movie. Okay, so simplest movie. For this example, we take omega to be the square. So gamma n is the rescaling of this square intersection with the lattice. Then the harmonic function will be just the first coordinate, and the initial state at all n will be just all two. Now, the first observation is very silly. It says that the movie phi n t, so this is the frame of the movie, simply converges as n goes to infinity. So for all t, it simply converges to just 2, a function which is identically 2. So, and this is kind of disappointing. So it means that your movie becomes a blur of the colors which average to simply a single color, which is 2, green. Okay, so, and now I had,
The way kind of to be expected given the integral that you have in the weak star.
well, this wouldn't be the case, I guess, for quadratic harmonics, the same holds for all two. But for cubic harmonics, you get already a kind of interesting quick star limit. You start getting again the fractals. So this is more of the consequence of linearity of physics. And so now I want to do something else. So, and this is the second observation, and which goes under the slogan, separate colors. So what do I mean by that? So if I foresee a value from 0, 1, 2, and 3, I want to define a characteristic function of that color on a particular state. So which means that it's just 1 or 0, and it gives 1 exactly when phi n, so at some point p, when at this point the value is exactly c. So you basically separate the color. So you just pick exactly that color, a characteristic power function of that value, if you like. Is it clear what I mean by that? And so
Maybe.
observation 2 is that actually zero color essentially never appears, so it converges to 0. Um, uh, uh, and the color 1 and the color 3 both converge to something more interesting, namely T and 1 minus T. And the color 2, well, it's not hard to guess from the previous remark and what I already wrote. So now I'm coming back to that remark that I made, is that at least from what I described, you can guess with what time you are. But you don't see the difference, let's say, between the time 1/4 and time 3/4. So they are same from this scaling limit perspective. Um,
You're doing weak star convergence all the time.
yeah. This is weak star, but we separate colors. And what I want to say that philosophically, to me, doing this kind of scaling limits is like making observations. So therefore, I wrote observation. But like taking the photos. But you see more things actually when you perform them, when you prove them. And so while proving what I wrote, which is very simple, we'll see more. We'll see that there is lots of structure. So for example, at rational time, there is some periodicity. At irrational time, there is some kind of stabilization. And there is a lot about patterns. So in there are patterns of 1 and 3 in the first half, or t less than 1/2. So 1 is always having 3 on the right, and the patterns of 3, 1 for t bigger than 1/2. So you always have this kind of patterns, and this is the way how you can distinguish between the 1/4 and 3/4. They are very similar. The average number of color is the same, but the patterns are reversed. Okay, so this is in terms of patterns. And so next time I'll be explaining exactly that. So this silly weak star results, and it's up to you to try it yourself. I actually encourage you to do it. And yeah, so this is morally the thing where the result itself doesn't reveal much, but proving it actually acquires you for you quite a lot of understanding. And then I expect that what I wrote here can be easily generalized. So for other harmonics, so I start to do it. But the idea would be to at least explore everything linear, and then probably quadratic. And cubic is really wild already. So, and I probably stop here. So are there any questions? We still have a couple of minutes.
Well, I mean, as you said, this even I could think how one would go about trying to show these statements. But
Yes.
just an observation that is a more general observation is that this convergence, for example, the one that you write there for x1, for chi1 of phi and t, this is a characteristic function for the number one.
Yes.
It converges, say for t less than 1/2. Let's say for t less than 1/2. It so you are letting n tend to infinity, and you're fixing t.
Yeah.
And you are getting something that sounds kind of funny, you know, because you are not getting an integer. You are getting just this.
Yeah.
When you.
So when you average how it appears, so this means that you have the density of ones. This is exactly this. Density
That's
of
right.
is T.
That's right. So that's the point, that this convergence has to be taken in that sense, you know, that, well, the definition is there with the integral, but it's not the sort of convergence that integers tend to integers, you know, you will get, you smear out the result, you know.
I forgot to say this is for T from 0 to 1. This is also.
That's right.
And it's periodic. So whenever you have harmonic, which is integral valued, the phi t is plus 1 is phi t. So.
So you'll smear out the result, you know. So it's, yeah, it gives you that kind of intuition, but then you say you will see at the patterns and get more information.
Exactly. So that's a general story with Sandpiles. Result itself loses a lot of information. And this is probably not the best way to compress it. So there should be a better way to express what you see.
And that's also an interesting question, how to say that.
Yes. To me, it's a real question about Sandpiles, how to state things. How to prove it is other story, but how to state it, I think it's wildly open.
Yeah. Well, thank you very much.
Yeah, thanks a lot. See you next week, or yeah.